Cool. Good morning, everyone. So thank you very much for coming to my talk. Docker has definitely caught everyone's imagination and everyone's attention, and it's definitely changed the way that we think about how we deploy applications and how we think about how we get started and scale up our systems from something running locally up to planet-scale systems like Google. But obviously, as Docker's evolved, other ways of thinking and other approaches and techniques have started to come about, and other technologies are starting to form which have different opinions and different priorities compared to what Docker provides. And fundamentally, containers are just Linux processes. So why do we need Docker at all? And this is what I'm going to be exploring with you over the next hour. So my name is Ben Hall. Please feel free, if you have any questions or any comments, to contact me via email or Twitter. I'm the founder of a company called Katacoda. Katacoda is an interactive learning platform for software developers. And we tell you and help you get started with cloud-native technologies such as Docker, Kubernetes, container networking, Docker security, container security, etc. And everything happens directly in your browser. So you don't have to worry about how to get started. You don't have to worry about installing or configuring anything. Instead, you can explore and experiment alongside a set of free interactive tutorial labs that we have on our platform. And we work with different companies like Red Hat who have taken our platform and extended it to help teach their user base how to deploy things such as OpenShift, which is their Kubernetes distribution. And so today, what I want to start exploring is what Docker provides to the ecosystem, and fundamentally what containers are, and why we can start building and exploring with different container runtimes and different container techniques. So we'll look at what actually happens when we run Docker run, what the different components involved are, and we'll look at how we can move away from needing a dependency on Docker and exploring other alternatives, such as how do we build container images if we don't have Docker involved? What are the fundamental principles? And also, how do we run processes without Docker? What fundamentally is a container? And finally, looking at the value this brings to an organization. So before we jump into that, let's explore why this is interesting, or why I'm particularly interested in this topic. So Docker has evolved for quite a number of years. If we go way back to when Docker was just being designed and prototyped, this is some of the logos which we could have ended up with. If you go into 99 Designs and look at the possibilities, and instead of having a nice whale, we could have had a beautiful giraffe. And obviously, Docker, since then, has evolved. We've got to know and love Docker as our container runtime. It helps us launch processes in a secure, scalable way, helps us deploy applications on both Linux, Windows, and ARM devices in a consistent experience, which is great. But Docker itself is also evolving. It's no longer just focused on launching containers. We've got how do you manage containers across multiple systems? How do you run things in the cloud with Docker Cloud, which has now gone away? How do you compose and orchestrate things with Swarm and Compose, etc.? And so Docker itself has evolved into a much bigger, much wider scope project. And to the point where actually Docker, i.e. Docker, the bit which runs containers, isn't called Docker anymore. It's called Moby. They have renamed the project to distinguish what the container runtime is, i.e. the components which go in to launching these processes in a secure way, compared to Docker Inc., which is all of data center and all of the more enterprise-driven feature sets. And so as such, when we're looking at running something very simply, i.e. I just want to run my process in a secure way, there's lots of other moving parts involved in having Docker in your stack. We have to take in other dependencies and use Docker networking and their opinions. And if we just want to run something very lightweight, we don't have a choice. We have to go all in. But there's also, because of this approach and because of how Docker structured itself, there's different security techniques. So Docker has a daemon. The daemon is what's responsible for managing all the containers on your system, all of the processes which are running, and it's basically the gatekeeper to your entire host. And as such, it's a sensitive part of the system. You should only allow trusted access to trusted processes and trusted users, because fundamentally you're giving them access to the entire machine. But when we look at how we go through the processes like building Docker images, we need to give things like Jenkins access to Docker so that they can go through and they can build our image that can then get rolled out. And so you'll see snippets like the top one where we run a Jenkins agent inside of a container because everything gets deployed as a container. And we pass in the Docker sock file. So this is how our container image can talk to the parent Docker daemon and use that in order to build these images. And so if we went in, we can do things like Docker build, and it will create our image. But we can also list all of the other processes on the host and list everything else running, which is potentially a security weakness. If we don't trust what is being built inside of our container, then they could potentially exploit the system in very interesting ways. But also, if we accidentally have a security breach, for example, we accidentally open Jenkins up to the world, which, if we do a quick search on the internet, is quite common, then we potentially open up our entire host to vulnerabilities and being exploited and being taken advantage of by Bitcoin miners and other such malicious actors. And so it's these kind of things where having to structure Docker and have this Docker daemon in place actually makes it more difficult to do things like build images, scale out our image across multiple systems, and actually have more of a secure system in place. And so this is the reason why alternative container runtimes have started, and the reason why I'm exploring how do we use containers and container images without having Docker in the first place. And so if we look at the alternatives available, this is Container Landscape, published by the Cloud Computing Foundation, CNCF. And so Cloud Native Foundation. And so we've got different projects inside of the foundation. So they're backed and they're controlled and governed by the foundation itself, i.e. Containerd and Rocket. Containerd is what Docker uses under the covers itself. This is how Docker, the CLI and the engine and the daemon, talks to the underlying system and starts our processes. It all happens via Containerd. But we've seen other projects spin up from different organizations. So Google last week announced gZizer, which is focused on how do you run a container with very similar properties to a virtual machine. So you have a different kernel, it runs in its own isolation space and its own process space. And so if your application did have a security weakness and someone did manage to break out of a container, they wouldn't interact and they wouldn't interfere and gain access to other containers running on your system. So ideal if you're running in quite a sensitive, potentially malicious actor style environment. And that's similar to Intel Clear containers, again, trying to introduce more of a VM-like property and security model into what containers can offer. And we also now have CRI-O, which is if you're deploying Kubernetes, having a container runtime which is designed for what Kubernetes needs. It's designed to solve that problem and only that problem. It doesn't interact with how do you do it on different systems, how do you orchestrate for different container runtimes. Instead, it's just delivering the needs that Kubernetes needs. And we'll explore more of this later. But actually, as containers have evolved, our ideas have evolved too. And so now you don't even need to rerunning your containers locally. Instead, you could use something like the Azure Container Service, and that could run all of your containers in the cloud. And because it's build per second, you can spin them up, do all of the workload which you need, and then tear them back down instantly. So it makes it ideal for ad hoc different runtimes. And being able to take advantage of that within our architecture can open up some really interesting opportunities. And for me, this is where the value starts to bring. When we start breaking our dependency and thinking and orchestrating our system around Docker and these kind of fixed container runtimes, we start seeing different opportunities which could exist within our system. And so we start thinking about, like, if we're running Kubernetes, we can have a container runtime which is focused on the needs of Kubernetes. So it's more performant, it's more stable, and it's more easily maintained by the open source communities in general, which should deliver a better, higher quality system because everyone's working on that one certain targeted problem. And we build a better system and a better design for continuous integrations. We can focus on how does that work within a CI/CD process. And instead of having our container runtime solve 20 different variations and 20 different problems, instead it's just focused on, right, how do we build the image in the quickest possible way? Because that's the problem which we're trying to solve. And this opens up things like cloud bursting and being able to easily run our container build on something like Azure Container Instances. And so when we start scaling out, we can push the workloads into the cloud instead of needing to spin up large virtual machines because we need that security model in place. And these are the things which we can explore. And the idea is that we could get to something which looks a little bit more distributed and has different container runtimes based on what our needs are. And so we could have Kubernetes talking to different container runtimes. So like, we could use libpod, which is CRI-O, and this could run our database. It's just running a normal container which we run every day. It sits there and it's happy. We could do something with a more higher security model for more sensitive parts of our system. For example, a public-facing web application. It's exposed to the outside, so if it does get breached because of certain underlying problems or security models which we haven't realized yet, and they get announced and zero-day attacks, then they still wouldn't be able to break out of that container, and they still wouldn't be able to interact with other things running on our cluster. And then because of things like these your container instances, if we wanted to have a scale-out kind of like distributed model which can scale up and down dynamically and dramatically based on workloads, we could use things like the virtual kubelet. And so that knows that when we give it a container to run, instead of it running on our local Docker host, instead it will go off to the Azure container instances and run the container there. And so this allows us to scale out things like message handling, message processing, or just scale out how our builds are being processed. And so different builds can have different characteristics, and they can run in different locations based on the requirements of our system. So if we're going to go down this path, and we're going to explore how do we do things without needing Docker, then what does Docker actually provide? And what actually happens when we do a Docker run and launch that container process? And so in this case, we've got a very simple hello world application. We're just running Redis. So we do Docker run Redis. So what actually happens when we execute this command? Well, the first thing is Docker will go off to the Docker hub, the Docker registry, where all of the public images are stored. And it will go to docker.io, library, which is a user, Redis, and pull down the latest image. So these are all just same default to what we have. And we could override these if we wanted to within our system and give like a targeted version of Redis, which we may want. But it will go off and it will download the latest version. So in this case, it could be Redis 4.0, and it will pull down the different layers involved. And this is the Docker image. So what is a Docker image? So if we look at what goes into creating this Docker image, it is encouraged that Docker images start life as a Docker file. The Docker file is a set of instructions which goes into how to configure and how to run a particular, and how to build a particular Docker image. So in this case, we're building a Node.js application. We're defining our dependency at the top, i.e. Node version 8. So that will go off, and that will use the Node version 8 Docker image. And then we're extending it with our own customization for our application. So we're adding layers on top of that image, which all represent a different configuration, different files which we need for our application to run. For example, going off to the NPM registry to download all of our dependencies, copying over our source code, and then setting some metadata. And this is where the layered technology and the layered approach comes in. Because fundamentally, all we're doing is adding on extensions to what came before it. And this is what we can explore in a little bit more detail. So if we go to what is a image. So what I'm going to aim to show you is what are the fundamental building blocks about how container images work, and what goes into the details. And so if we come into and enlarge this slightly. So let's go through that example of pulling down the Redis image. So now we're pulling down the different layers which went into building up that image. And all of these layers together create our structure. So one layer could be the base operating system, another layer could be the Redis binaries, and another layer could be the Redis configuration. If we break it down, we can actually explore what this image is. We can do Docker save, give it the name of an image, and we can save it into a tar. Because fundamentally, all a Docker is a zipped, a tarred up directory. And so we can explore and extract that tar file. And you can see that we've got all of the layers which went in and what we downloaded, we can now explore the details of all the files under the covers. And so fundamentally, all we're doing by doing a Docker pull or a Docker run is download this tar file and have it extracted into the Docker data directory. And if we look at what's in this directory, we've got our directories, we've got some metadata about repositories. So this is saying like what repository exists, what the version number is, and what's the tag, the SHA for that image itself. We've got manifest.json, which again gives it some more context, some more data around how that image got built and the different layers involved. And so this gives Docker all of the information it needs to launch the container runtime. But fundamentally, at this point, all we're doing is creating 2 JSON files which represent our container. And if we look at something like, oops, that's not stored. If we look at what's inside of an image, we can see that it's another tar file. So it's a tar containing tar files. If we extract one of those tar files, we can see that it's all of the different components which went in and were built as part of that layer file, as part of that Docker kind of layer. So if we go into this directory, so yeah, it got extracted. So we can now look at what's in XCD, and we can see it's got the package manager, and it's got the world, and we can kind of output and explore these directories. So fundamentally, all we've done is that Docker file, what we were doing is defining the different layers, i.e. copying over the files required into each of these tar directories, and zipping them all, or tarring them all up into a single repository, and then pushing that into the registry. What this means is we don't really need a Docker file to build this structured image. Instead, we can do it all manually if we wanted to, because fundamentally it's just a well-structured tar. So in this case, what we're doing is tarring up an empty directory, and then passing that into Docker import, and now we have, and give it the name empty, and so now we have the smallest Docker image possible. Docker image possible. And so it's got all of the metadata which it needs, but it's just empty. And so this is the starting point of every single image. But we can actually build something more useful based on these techniques. And because all we're doing is creating these files, we can create an image manually using different approaches. So in this case, we're going to take BusyBox. BusyBox is a very small, lightweight distribution, Linux distribution, ideal for running inside containers because it's got a super small, low footprint. And so in order to kind of like bootstrap BusyBox, there is, let's do it in a different directory to make it easier. So we've done that. So we have this kind of shell script, and when we run it, it will go off and it will download BusyBox and the binaries, and install it and copy it into the directory called BusyBox. And so this is the entire operating system. It's a grand total of 1.9 meg. And if you actually look at what the operating system is, it's just a single binary called bin. And if you list what the bin is, all of the things which we know and love within Linux, so like ls, df, free, make directory, all just get pointed into the single one binary via a symlink called bin/busybox. And so that's how it's managed to make it so small and so compact. It's really quite cool. So we can take this and we can build our own image from it. So if we go up again, so we have our BusyBox. So we can add in our own files. So in this case, we're adding a release directory. Sorry, a release file called code private build. We want to extend our image to include that. And so just as we did with creating the empty image, what we can do is zip up that directory, zip up that BusyBox directory as a tar, or kind of tar compress our directory, pass it into Docker import, and so Docker will then convert that tar file into a Docker image for us. And so now we can do Docker images, and we have our beautiful BusyBox image created. which we can run and get out our file. And so without needing to create the Docker file, without needing to go through the traditional steps of Docker run, we can still get the benefits of having a Docker image created. And so by having this, we can explore alternative ways of building it. We don't need to go through the traditional approaches. And we can use different tools and different approaches based on what our needs are, i.e. this can now run somewhere like the Azure Container Instances platform. And the reason this is, and the reason this exists is because the structure which we're working with, i.e. creating these tars, creating these repositories.json, the layers, are all based around an open container spec. This has been created originally by Docker. It was donated to a foundation. And so now anyone involved can create container images which can run on any other container runtime. We don't have to be kind of specified and fixed into one, so we don't have any lock-in. So we can explore and go to different approaches. And this is where the whole idea around a daemonless builds come in, so that we can move and scale up differently. Two popular ones at the moment is one from Red Hat called Builder, and another one from Jess, who works now at Microsoft, previously Google, Mesosphere, Docker, and she does awesome work. But the idea being is how can we run and build our images in a simple, lightweight way, which adhere to the specifications defined so that they can run on Docker, but we can run them anywhere. And we can run them without needing privileges. We don't need a full VM. We don't need all of the permissions which you need. Instead, it can be something lightweight and available to everyone. And the idea is that this will be compatible with our existing ways of working. So if we come back and have a quick demo, if we look at something like image, and wait for Coda. So what we have now is we've got our container runtime, our machine. It's got the image binary installed. We can download kind of our Docker, kind of like an example directory, which has got a Docker file. We can call build on that. And it will look and feel very similar to what we expect from Docker build. The main difference is that we don't have a Docker daemon installed. It doesn't have the Docker processes running. And it doesn't require an entire virtual machine and all of the permissions from an entire operating system. Instead, it runs using rootless technologies and no privilege technologies. And so we can run these builds in a much more secure way, which is ideal when our builds are slightly more entrusted. And this will go through, it will do everything which a Docker build does. I create that tar file fundamentally and these layers, and then we can push that to a registry, and it will work in exactly the same way when we roll it out across our system. So this is really cool, and it's really interesting ways and directions which we're heading. So that's how we can build an image. We can build an image using different technologies, and that can now give us something which we can run. So what happens when we want to run our process, i.e. Windows, Linux, or ARM? What happens under the covers? And fundamentally, at this point, Docker has taken the fundamental principles which are available in the kernel. They've packaged them together in a really nice, appropriate way, and they've made it accessible for everyone to build upon, i.e. what we do today. And if we look at the Docker engine and then different components, so we've got our command line interface, i.e. Docker run. That goes off, and that talks to the Docker engine and executes our commands. Under the covers, the Docker engine talks to the technology called containerd, i.e. The project looked after by the CNCF, and so completely independent and available to everyone outside. It's not owned and coordinated by Docker. It's coordinated by the community. And then that will talk to another technology called runc, and fundamentally runc is what starts the process in a nice containerized way. And because it's running inside this containerized process, it's running as a container, it's secure. And by secure, I mean we can add certain restrictions about what that process is or isn't allowed to do. So we can restrict how much memory it's allowed access to, what other processes it can communicate with and see, what devices on the system it's allowed to access. And we can lock it down as much as possible. But fundamentally, our containerized process, which Docker run, is still a running Linux process. And so if we take our Docker run command, for example, after that container started, we can list all of the processes on our system, and we see that we've got this Redis server running. It's owned by user 999, so it's running as a non-root user. Again, low privilege, secure by default mentality. And it's got all the PIDs and the processes which you would expect. Under the covers, we don't need to use Docker for doing this. We could go to run C, launch our container, and again, that launches it just as this process running on our system. So what actually goes into a Linux process? What is actually Docker doing under the covers at this point? So the first thing we need to know if we want to explore this some more is we need to identify the PID, i.e. the process ID of that container, so we can start exploring what's actually happening under the covers. And so if we run docker top, give it the container name, it will return the top information just for that one container and all of the processes running inside of that containerized process. And so he gives us two important IDs. One is the PID, and one is the parent PID, i.e. which process started and launched this containerized process. And so in this case, the PID, the process of our Redis server is 537. And so now we can explore what's happening. Like, how is that configured? And so all the processes on Linux live in a directory called proc. Proc is the heart of all the Linux processes and has all of the information about everything on our system. And so if you list the contents of proc, you'll see things like 1, 10, 11, 12, i.e. all of the process IDs which are running on our system. So 1 being systemd or the init system, and now also all of the other things like our container, which is running. And if we go into that directory, we'll see lots of files with strange random names, but they all have a certain targeted purpose. And so we can start exploring these. So for example, if we look at the exe directory, or kind of file, the exe file is a pointer to the process which has been launched. And so we can find out the underlying process that PID is related to. So in this case, the Redis server. We can look at the command line, i.e. what command line was used in order to launch this process. We saw from top it was the Redis server and the port number. And we can also start exploring things like the environment variables. So what environments are set on this process? The reason this is interesting is because we can start changing and modifying these files. These are just standard Linux principles. And so when we do a Docker run, we pass in an environment variable flag like a hostname or kind of like a password. That password is actually defined within this file. And when the process running is configured and asked what environment variables am I aware of, the contents of this file is what the process has access to. But this is also how all of the security models within that containerized process are configured. And so one of the examples of how a container is actually contained, or how a container process is actually contained, is using control groups, i.e. C groups. And C groups restrict how much of a resource the process is allowed to access. So for example, it will control how much memory that process is allowed to utilize. And that value is a file stored on disk within the process directory. And so in this case, what we're doing is we're looking at the CPU shares, i.e. how much CPU is that process allowed. But we're also modifying the memory usage within that process is allowed to access. And so we're echoing 8,000 or 8 million into the file called memory.limit in bytes. Linux under the covers will happily convert that into the proper value and not that 8,000. It would convert it into actually the correct byte value. But now if we look at the stats and the information about that container, we can see that the process has been limited. And we change it and we increase it, we can see that value increase alongside it. And so we can start changing and modifying the security models of any process within our system, whether it's been started by Docker or not. And this is fundamentally how people like Google and Heroku and all of the other technologies were able to run processes in a secure container way before Docker existed, and how Docker actually gets its security model. And so another technique is namespaces. Again, namespaces are just references and pointers on disk. And so we can explore, we can navigate and see what namespaces our process is attached to, and how that security model is applied. So the mounts, the PID namespace, the net namespace, and how we can ensure that that process has a different, sees a different entry point and view of the system than anything else running our system. So namespaces allow us to limit and segregate each process so that they can't communicate with each other, ensure that they get different process trees. And so we list a container, it only sees what processes that container actually has access to. And that's all done via the namespace. And then the final key aspect of Docker security and what makes a container contained, or a process contained, are three techniques: AppArmor, SecComp, and capabilities. AppArmor is the first one which we see. So we can look at any profile which has been defined to a process. And in this case, we've got the AppArmor profile Docker default enforced. And so this means that the AppArmor profile has been applied. The profile is basically defining a list of rules around what that process can or cannot do. And so you can define a rule saying a process is allowed to send TCP packets, but it's not allowed to send raw network packets, i.e. it's not allowed to send ping commands to the outside world. Or it's allowed to write to the opt directory, but it's not allowed to write to bin, XC, home, etc. And this profile is designed to represent what a normal functioning application is meant to be able to do. And if the application goes outside of this, then it's not functioning and it's not allowed and it's restricted, and I'm designing this secure profile. The next technique is SecComp. So SecComp is similar, but it's designed to restrict which system calls a process is or isn't allowed to make. So within Linux, everything an application does fundamentally gets boiled down to 330-something system calls. And so these system calls are things like opening a file, changing modifications, checking if it's got access to read, closing file pointer handles, fundamentally the underlying primitives of everything. Now, most of these system calls are happy and kind of safe for processes to call. Other ones are a little bit more sensitive, i.e. they allow processes to install kernel modules, or they allow them to mount additional disks, install additional network devices, etc., which are a lot more sensitive and something which we wouldn't want our process potentially to have access to. And so by using SecComp, we can restrict what system calls that process is allowed to make. And so this is how we can start enforcing a better security model. And finally, we can look at the capabilities. Now, capabilities are groupings of security techniques, a grouping of functionalities that exist within Linux. So for example, can I change the system time is a capability. And then you can define whether a process is or isn't allowed to do that capability, i.e. is it allowed to change the system time or not. And there's many different capabilities, and they're all stored in an interesting bit mask. And if we decode that bit mask, we can see all of the processes and everything that container is or isn't allowed to do. And because all of the primitives that we have are in these raw containers, it means that in order to launch a process in a different security model, all we need to do is know how these processes, these files are put together, and how to correctly change them when we need to. And this is how we've got different container runtimes which have emerged. To the point where if we wanted to create our own container runtime, we could do so in roughly 23 lines of code. So this is an example from Liz Rice. She's a developer evangelist at Aqua Security. And she uses Go in order to create the most foundation, simple, lightweight container runtime possible. And we can see that, actually, if we go through it line by line, we can see that it is launching a process in a different security model than normal, in a more restrictive security model. And so it's configuring the C groups, i.e. how much resources is this process which is going to be launched allowed to access. It's setting some PID limits so that it can't, how many processes is that process allowed to fork and launch under the covers. It's setting different mount directories so it can get access to certain properties. It's changing the root, the root. So instead of having access to everything on our disk, it only had access to a certain directory, i.e. this is how Docker changes the root of the container to point to that Docker image directory, and that's how the container processes work. And it's these kind of techniques which allow us to launch and use different container runtimes. So if we have a look at how do we launch a container, a contained process, we can look at something like Podman. Actually, let's do what is a container. So what we're going to do is we can run like our contained process just to see kind of some of the techniques under the covers. So we can get the PID limits or the PID ID, which is 1161 in this case. We can see the process tree of that and like what went into actually launching it. So this is the process. It was launched by Docker container D, which was launched eventually by Docker D. And so we can see how that process went in to being launched. And now, because everything's in the proc directory, we can explore it. We can, if we do that, and explore it. We can see all of these files. We can explore them, i.e. what environment variables have I been defined, etc. So we have these namespaces which get attached. So if we look at directories, a cat net, don't escape that. So we have all of our the net, the network interface, network component, etc. And what we can do is we can launch via the network namespaces, that's what I'm trying to go for, and we can launch processes attached to these namespaces which can be shared. And so we can do PS. And so now what we're doing is using unshare, which is the technique of launching a process which has been attached to other containerized processes. And so in this case, we're using unshare. We're telling it to launch a new process. We're telling it to have a separate PID namespace, telling it to mount the proc directory so it knows how to launch, and then launch bash. And fundamentally, that is kind of a contained process. It's running its own namespace. It can't access anything else running on our system. And that is the fundamental starting point to how we can launch these processes in a secure, containerized way. And it's these techniques which go into building our containers and what Docker is actually doing with C groups, AppArmor capabilities. That's what I wanted to show. So, what about other container runtimes? So if we have a look at Podman. So what Podman is doing is he's taking all of these primitives of what's available within C groups and building them into an alternative container runtime. The main difference is we don't need anything installed on our system apart from the Podman CLI itself and run C, and we don't need a daemon running to manage the processes. Instead, the processes are just running in this containerized way by taking the techniques of configuring these C groups and configuring these capabilities. So if we do Podman run, we can give it the same Docker image, because fundamentally a Docker image is a container image based on a spec, and so it can run anywhere. All we need to do is download and extract that tar file. And we can launch a process, because fundamentally all the process is a Linux process with different C groups, namespaces, and the proc directory configurations defined. So anyone is able to do this, i.e. Podman. And all it's doing is the CLI is a wrapper over the top of these processes which are running on our system. So in this case, it will list all of the processes running which have been started via Podman. But if we look at the process tree, if we do psax grep app, ps tree, let's see how good my memory is. The process tree is a lot smaller and a lot more focused than what it was before, because we don't have these daemons hanging around which are controlling that application. And so now we don't have to worry about what happens if the daemon crashes, because it's not going to kill all of the processes which it launched, because there is no daemon process in place. It's just the same as if we just ran PS or kind of like any other process on our system. Podman is just running that process and configuring the security models around it, making it a very lightweight, very streamlined way to launch processes on any system. And this is the idea we have with different container runtimes. We want to take it back to the bare principles. Once we have that in place, we can start exploring different security models. And so this is where we start seeing things, an alternative container runtime start popping up, like Kata containers or Windows Hyper-V containers. They just take that process, they can launch it within a very cut down, very lightweight, streamlined virtual machine, so that you get a different kernel, so you're not sharing the same kernel, you get a more secure bounded context, and as such, if a process does get broken into and exploited, if they do manage to break out the containers, they don't get access to everything else on our system. So again, why is this important? So this becomes critical when we look at things like Kubernetes. Kubernetes itself is a container orchestration. It's designed to run, manage, and control all of the processes across our deployments. And Kubernetes is great. It's been building on top of Docker, and it's taken advantage of all of these container technologies. The problem becomes when Docker wants to go down a certain path and a vision and how they want their API to be structured, which is particularly not aligned with the vision of how Kubernetes wants things to be running. So for example, if you've ever run Kubernetes and you've looked at what's running, you'll see lots of pause processes running. And these pause processes is because Kubernetes structures everything around a pod, concept of a pod where you can share the network interfaces, the volumes, different security aspects of a container together. You can have multiple containers which can all act as if they're on the same machine. But Docker doesn't have this concept of a pod, so they've kind of had to create kind of these abstractions to represent how they want Kubernetes to be structured in an ideal world. So instead of that, they're going down a different path and allowing support for different container runtimes, one of which is CRI-O, which is designed with Kubernetes in mind and designed to be aligned with how Kubernetes is operating and keep it very small, lightweight, and streamlined, and so that when Kubernetes is upgrading and making changes, CRI-O is there to support it. And it works almost in exactly the same way, but it's a little bit easier for the community and operators to manage. And so we look at getting started. So if we do Kubernetes init, if we enlarge that, so kubeadm init. So kubeadm is a way to bootstrap a Kubernetes cluster. And so what it will do, it will go through and set up things like certificates so that all of the different Kubernetes processes can talk to each other, set up all of the different configuration, download all of the container images required in order to launch it. And so by default, this will go to Docker, and it will do everything via the Docker API. But now we've started having these abstractions and supporting different container runtimes, i.e. Kata containers, gZider, Docker, and CRI-O. And so when we do it, what we do is we point it to a different container runtime interface, i.e. in this case, CRI-O socket file. And so now instead of kubeadm and Kubernetes initializing itself on top of Docker, it initializes itself using this as a process. And so if we clear this, if we look at Docker PS, we don't have any containers running. If we do Kubernetes runtime interface control, PS, we can see all of these processes which are running. And compared to what it looks like when we do Kubernetes and Docker, which is lots of pause containers, lots more noise, instead we have a much more focused experience. We can see the processes that Kubernetes requires, i.e. the API, the control manager, the scheduler, so that these things can be launched. And it's much more focused on how the Kubernetes experience is designed. And so these will launch, and we can interact and we can control and view the processes in exactly the same way as we would before. And Kubernetes is being open and transparent to supporting these different container runtimes. So if we look, we've got our master running. We can describe the master and get the container runtime version. And so now that will support and be open to different platforms based on what our needs are, which we'll describe. And for example, what does this mean? So what it means is when we look at things like the Azure container instances, we want the ability for Kubernetes to be able to schedule different types of workloads, be that Docker containers running on our host, container runtimes in that secure, more containerized, sandboxed way with things like Kata containers and Hyper-V containers, but it also allows us to scale up to things like Azure container instances. And to make this easier, Microsoft have built something called the virtual kubelet. And so what we can do is we have our different Kubernetes nodes within our system. They know how to launch containers according to the different container runtimes that we specified and the different security techniques that we require. But this virtual kubelet also knows how to launch containers on different systems, one of which is the Azure Container Instances service. And so if we wanted to scale up, we can have the virtual kubelet go off to the API, deploy the process there, workload happens, and then when it's finished, it gets teared back down again. And so by thinking differently and thinking beyond the scope of, right, we have Docker and we have processes, and this is how we launch things, we can change how our architecture happens within our system. And as such, we can start exploring new alternative ways of deploying and managing our system. And so the demos which I showed you are all available online. If you go to Katacoda, I've got demos and scenarios which walk you through what a container process is, which I showed you and explored today, how to build images, and how to get started. And for me, I find this really interesting because it allows us to build systems that are appropriate for our needs. It allows us to build systems that are designed to solve particular problems, like all I need to do is build container images in a secure way. So instead of having to worry about the entire the Docker stack, instead I can just use image and a command line tool, which will go ahead and build that one image process for me and allow me to run it anywhere because we don't need the security model of running an entire containerized system. And this also takes things like cloud bursting builds, which I think are going to be a great advantage in the future, and so that we don't need to have these big, heavy virtual machines hanging around. Instead, we can just have processes running within these serverless foundations and serverless technologies. We'll see more of this happening over the future, and more of this coming, but at the moment today we have things like CRI-O, we have Podman, so that we can run these processes in a containerized way, and we have different ways of building, so builder, images, and more are coming soon, particularly from Google. So I hope you found that interesting. It's an insight into what's coming into the future and how I think the landscape is changing. If you have any questions, then please do email me or tweet me, and with that, I hope you enjoy the rest of your conference. Thank you.